Hey there, cats and kittens. Welcome back to the second half of lesson 4.4. In chapter 4, we've already learned about tangent planes, but I want to warn you that they do not always exist. I have the piecewise function that you see on the screen plotted as this blue surface, and upon inspection, it looks fine. Nice and smooth, looks very continuous. However, right at the origin, where we have this white point plotted on our surface, it almost looks like the surface has been pinched. So we're going to investigate at that spot. If we were to travel along our surface as it intersects the plane x equals 0, we can see that we're traveling along this pink line. And if we were to travel along the path y equals 0 on our surface, we would travel along the green line. Each of these are essentially just the x or y axis. That's where the surface intersects those planes. And they both seem to be fine. If we were to find tangent lines to each of those surface intersections, we might think that the tangent plane should be the xy plane, for example. However, if we were to travel along a different path, in this case we traveled along the two simplest paths we could, they both led us to the origin with no problems. Both of those curves, the pink and the lime green, looked completely differentiable. No corners, no jumps, no discontinuities. But if we were to pick a different path, like maybe the path y equals x, and we see how that intersects our surface, we can see that this almost looks like the absolute value function. So this yellow line drawn out on our surface, that's the intersection of the plane y equals x and the surface z. And if you look on one half of that yellow line, the slope is negative. On the other half of the yellow line, the slope is positive. And we can see right there at the origin that it makes a sharp V, and otherwise known as a corner. If we wanted to find the tangent line to that yellow line at the origin, it doesn't exist because we know corners are not differentiable. So essentially what's happening here is we're trying to find all the tangent lines through that white point. The first two we found totally agreed with each other, but the third one that we found contradicted the rest. So in this case, we are able to find quote-unquote tangent lines, but they don't all live in the same plane. Therefore, this surface does not have a tangent plane at the origin, which means this surface is not differentiable at the origin. So if you can't find the derivatives, then it's not differentiable, and if you can't find the derivatives, then you can't find tangent planes. In the case where you can find tangent planes, then we can introduce the idea of linear approximation for these surfaces. Back in Calc 1, hopefully you remember seeing linear approximation for the first time there. This is a quick recap of the Calc 1 linear approximation. If we have a function f of a single variable x, and we know it's differentiable at the point x equals a, we can draw a tangent line to that function. So we have the blue curve showing on the screen. I'm going to show the tangent line, which is the red curve. That line is tangent at the point x equals a, y equals f of a. Linear approximation basically takes a point from the tangent line and matches it up with our hypothetical point on the curve. So I have a red point on the tangent line, a blue point on the original function, and notice that they're pretty different. The red point looks like it's on the x-axis, the blue point looks like it's above the x-axis by 0.5. But maybe that's because we're just too far away. If we were to move these points closer to the gold point, these two points become closer and closer together until they're nearly indistinguishable. And this is why we use the tangent line for a linear approximation. We call it linear because it's a tangent line, and we use this to approximate the values of more complicated functions like 1 over x, for example. So in Calc 1, we used the tangent line to make approximations, but in Calc 3, we're going to use the tangent plane. And if you look at the function L on the right-hand side of the screen here, this is definitely the equation that we were using for the tangent plane. Notice that we're using the notation L of x and y. This is saying that the linear approximation, we're calling that L, it's a function. And we can calculate approximate values for f using the function L. L is defined to be the tangent plane. If we want to use this idea on a function like the square root of 41 minus 4x squared minus y squared, if we wanted to approximate the function value when x is 2.1, y is 2.9, we can do that by first calculating the equation for L and then plugging in our values for x and y. So if we are working with L of xy, we need to know what our function is at that x0, y0 point. We also need to know what the partial with respect to x is at that known point, and we're going to multiply that by the change in x. And then we need to know what our partial with respect to y is at that known point, and then we'll multiply that by the change in y, not x, but y. The second y almost became an x. Okay, so let's work on this piece by piece, just like we did in the last examples. We need to calculate one at a time. We are using 2, 3 for x0, y0, so we need to calculate f at 2, 3. We also need to calculate our partial derivative, and then we need to evaluate that at x0, y0, so we're going to find the x partial, and then we're going to plug in 2, 3 to our x partial. And then we need to find our y partial, and then we'll evaluate that y partial at 2, 3 as well. Go ahead and try each one of these calculations, pause the video, and then match it up with what I show you in just a second. So we've calculated the function at the point 2, 3, found that to be 4, so we're going to plug that into our L function. We've calculated the partial derivative with respect to x at 2, 3. We found that to be -2, so we'll plug that in up here, and then we calculated the partial with respect to y, evaluate that at 2, 3, and plug that in right here. So once we plug all of those things in, our L function of x and y is equal to 4 minus 2 times x minus x0, which is 2, minus 3/4 times y minus y0. y0 is 3. Once we simplify this a little bit, we can combine some coefficients here. We end up with 41/4 minus 2x minus 3/4 y. That is our linear approximation function. So now that we have this, we can plug in any value for x and y and use this linear function to approximate the value. So now let's go ahead and do this. L at 2.1, 2.9 is equal to, we're just going to plug in for x and y here, Go ahead and type that up into your calculator. And it should simplify out to be about 3.875. So that's the linear approximation for the surface F at the point 2.1, 2.9. So this is our approximate value. If we want to, since we do have the actual definition for our function f, we can compare our approximate value to the actual value. So f at 2.1, 2.9 should be fairly close to the value 3.875, but let's check to see how close. Type that into our calculator. And I get some decimals that don't want to stop, so let's go ahead and write that we have even here an approximate value, which is about 3.8665, which is fairly close to what we have from our linear approximation. In fact, the error is only about 0.2%. Now notice that 2.1 is very close to the value we used for x0, that 2.3 value. And 2.9 is very close to the value we used for y0, which is 3. Because these are very close, our approximation should be very close. However, the further we move away from these points, x0, y0, our linear approximation will start to become questionable. So if you recall the visual for linear approximation from the Calc 1 review, as the points were further and further away from our anchor point, the approximation from the tangent line compared to the actual function was a little bit off. They were further apart, but as we moved those points closer, they became closer to each other.